Hello viewers, Wagadar taking you through the story for A-Level Physics Paper 1. And in this video, I'm going to go through the marking guide of Physics Paper 1 of U.A.C.E Uneb 2020. So this video is suitable for students in both Senior 5 and Senior 6 offering physics. Now, where necessary, the following constants would be used. So we shall start with question 1. Question 1, part A, Roman 1 says, state the laws of static friction. So here they specified static friction. Remember, there are two kinds of friction. There is dynamic friction and static friction. So sometimes they will not specify, but this time they have specified. So you have to only consider static friction. So you come and say that friction of force, that is the first law, friction of force opposes attempted relative motion. Now this word attempted is there because they only said static friction. So always remember that this word attempted has to be there. So friction of force opposes attempted relative motion between two surfaces in contact. Now we use the word attempted because the bodies are not yet in motion. They are just at the point of moving. Then the second law says friction is independent of the area of contact of the surfaces provided normal reaction is constant. So this condition has to be seen. Then the third or the last law says limiting friction of force is directly proportional to normal reaction. So directly proportional to normal reaction. And those are the three laws that gives you the 3 marks. So now shall go to part A, Roman 2. Roman 2 says use the molecular theory of matter to explain the laws stated in A Roman 1. So you start with first law. First law, you come and say that the surfaces in contact rest on each other's molecular projections. You know this word, molecular projections. So what does that mean? It means that the actual area of contact is very small, and this leads to very high pressure at these points. These points form cold welded joints. So the word welded is in quotes because it may be misinterpreted. So remember to put it in quotes. So you come and say that to conclude that the surfaces to move relative to each other, a force must be applied to break the welded joints. So that's how marks would be applied. That is for the first law. Now let's go to the second law. So the second law shall say if normal reaction is kept constant but the surfaces are made to rest on a small area, fewer points of contact will result. This will cause higher pressure at these points and hence they tend to flatten out, restoring the actual area of contact to the initial value and hence keeping frictional force constant. So that explains the second law, because we said frictional force is directly proportional to normal reaction. Therefore, when normal reaction is constant, frictional force must be constant. So now we shall go to third law. Third law shall say that as normal reaction increases, the pressure at the weld also increases. and this causes the points to flatten further and the actual area of contact, so this word is area, the actual area of contact increases, hence an increase in friction. So basically that is the explanation for first, second and third law using molecular theory of matter. So now we shall go to part B. Part B says, describe briefly how to measure the limiting friction between a wooden block and a plane surface. So we shall start by drawing a sketch diagram to help us ease the explanation. So we shall label the parts. This is the horizontal table, that is the wooden block, and that is the smooth fixed pulley, inextensible string, and scale pan, masses added to the scale pan. So that is the setup, and the setup is as shown above. Then we shall start the theory part, where we shall say that known, you can say known or small, any of the two words is okay. So known masses are added onto the scale pan in bits until the block just starts to move. So those two words are needed. However, that when it just starts to move, just means that it is at the point of moving, it is not yet in motion. Then it shows that the total mass M of the scale pan and its content is measured and recorded. So M denotes the mass of the scale pan together with all its content. Limiting friction is given by mg. So remember, they wanted only limiting friction. Some students confused it and they went further to get coefficient of limiting friction, which is not okay. So that's how the 4 marks would be awarded. But there is also another alternative experiment, so let's also look at it. So in this case, we need an incline. So in this, we shall say that a block of mass M is measured and recorded. So this is the block. The block is placed on a horizontal surface. So this here, there is a tilt, there is something like a pivot, say that this plane can be raised or can be adjusted. So when the block is, when this surface or this plane is still on the horizontal, that is what they mean. The block is placed on the horizontal surface. The plane surface is gradually tilted until the block just starts to move. So in this diagram, they have shown when it has already been tilted to a certain angle theta. So it is gradually tilted until the block just starts to move. So this word just is very, very vital. So when that point is reached, the angle theta between the plane and the horizontal ground is measured and recorded. Then we shall conclude that the limiting friction is given as mg sine theta. So remember, they only wanted limiting friction. Some students went further to get coefficient of friction, which is not required. So that is how the 4 marks would be awarded for this alternative experiment. So that was part B. Now we shall go to part C. Part C says, a block of wood of mass 3.9 kilograms rests on a horizontal table of height 5 meters at a distance of 6 meters from the edge of the table. A bullet of mass 50 grams moving with a horizontal velocity, notice what, horizontal velocity of 500 meters per second, hits and gets embedded in the block. If the coefficient of dynamic friction between the block and the table is 0.3, Roman 1, find the initial velocity of the block after collision with the bullet. So I think let's start with that. So you have first let V1 be the common velocity just after collision. So this word just is needed. By the principle of conservation of momentum, we shall say that momentum before, total momentum before is equal to total momentum after. Then we shall come and substitute. M1 is this. So 50 grams is 50 divided by 1000 to get in kilograms. That is why there is 0.05 here. Then this is the velocity, which was 500 meters per second. Mass of the second one, it was 3.95 kilograms, and the velocity, it was initial at rest, so it is 0. Mass of this, mass of that, then this is the velocity they want. So when we make V1 the subject, V1 will be equal to 6.25 meters per second. So that is how the 2 marks would be awarded. So now we shall go to part C Roman 2. Part C Roman 2 says, calculate the horizontal distance from the table to the point where the block hits the ground. So this question is easily done with the help of a sketch. So let's first draw a sketch. So we have the horizontal ground, then we have the table, and the table was 5 meters of height, 5 meters above the ground. So you have put there 5 meters. Then you have put there a block of mass 3.95 kilograms. Initial at rest, that's why there is a velocity 0. Then you also have the bullet, which is of 50 grams, which is 0.05 kilograms, and the velocity is 500 meters per second. So it moves up the edge of the table, and at the edge of the table, remember, it gets embedded. So in this point, the mass is the total of these two. Therefore, when I add this with this, I'll come up with 4 kilograms. Therefore, the total weight will be 4g, and to act vertically downwards. Normal reaction will be R. Forward force is 0 because they didn't talk about any force pulling the system, so that is why there is a forward force of 0. Then the body is moving that direction. Remember, this surface is rough, therefore friction must oppose motion. If motion is in this direction, friction must act in this direction. So let's put it there, and it will be mu r. So they say that this body continues to move until it hits the ground. So that path is called a projectile. So let the velocity at this point be v2. Remember, v1 was the velocity just after collision, but it moves until it reaches the edge of the table with another velocity, which is v2, and after that it continues to move freely under gravity up to this point. And that path is called a projectile. So the distance is this which they want. So you can say that frictional force is mu r, and the normal reaction is mg, which is 4g here. So I'll come and substitute mu, which is 0.3, m is 4 kilograms, and g is acceleration due to gravity. In physics it is 9.81. So you come up with 11.772 newtons. Then you shall say that let v2 be the common velocity at the edge of the table, which is that. Therefore, from work energy theorem, work done by the resultant force is equal to change in kinetic energy. Why? Because you have to first get this v2 before we consider this projectile. So the aim is to first get this V2. So we shall use the work energy theorem, which says that work done by the resultant force is equal to change in kinetic energy. So kinetic energy is going to change from V1 up to V2. That is the velocity. Velocity changes from V1 to V2, and the resultant force will now be, I think we'll see this, forward force is 0 and opposing force is mu r. Therefore, resultant will be 0 minus mu r. Reason being, resultant force must act in the direction of motion. So half a mark for getting friction. Then we shall go and substitute in work energy theorem. So force, resultant force is that, distance moved is s, kinetic energy, change in kinetic energy will be a half m final velocity minus initial velocity, but remember to put the squares. Then next we shall substitute. 0 is there, f is there, s is there because they told us that the distance moved will be 6. Then mass is the total, which is there. Final velocity is what we want. Initial velocity was got as 6.25. Then when you use the calculator, we shall simplify, and then I think realize that we have only V2 as the only unknown. Therefore, V2 squared will be that. Therefore, when I put square root on both sides, I'll get V2 as 1.9356 meters per second. So now that I've got V2, I can now consider the projectile. So let V be the common velocity with which the block hits the ground. For vertical motion, we have the equation that y is equal to a half gt squared. Why? Because the entire velocity is horizontal. If you look at this, at this point the entire velocity at the start is horizontal, meaning that the vertical component of velocity is 0. That is why the ut is not there. So it is just y equal to a half gt squared. Then you shall substitute for y, which is the height, substitute for g, which is 9.81. We have t as the only unknown. So when I simplify, I'll come up with t squared being t5 equal to 4.905 t squared. Then t will be 1.0096 seconds. After getting t, I can now consider horizontal motion, where x is equal to v2t. Come substitute for v2. V2 is this and t is this, so we'll come up with the distance required as 1.9542 meters. So basically that is what they wanted, and that's how the marks would be awarded. So that's how the 5 marks would come about. So that was question 1. Now we shall go to question 2. Question 2, part A, Roman 1 says, part A says, define the following as applied to materials. Roman 1, stress, and Roman 2, Young's modulus. So stress is the force. You can either use the word force or use the word thrust. So stress is the force acting on a cross-sectional area of 1 meter squared of a material. So that was stress. What about Young's modulus? So Young's modulus is the ratio of tensile. So we need to see this word. Tensile stress to tensile strain of an elastic material, provided Hooke's law is obeyed. So this condition is needed. Remember, this word tensile has to be seen. So that was part A. Now we shall go to part B. Part B says, the velocity of compression of waves traveling along a rod made of a material of Young's modulus E and density rho is given by this. Show that that formula is dimensionally consistent. So they need dimensions. So left hand side we have V dimension, so it has to be in box brackets, so the symbol has to be in box bracket, but the dimension should not be in box bracket. So this box bracket means that you are getting the dimension of this V, which is, remember, velocity is meters per second, therefore meters is denoted by this length, which is capital L, per second is this t to the power -1. Then right hand side we had this formula, so this was Young's modulus, the units are those, the dimensions are those, then density, the dimensions are those. So next is to use the laws of indices to come up with this. So this one, you realize that this m cancels, then this L and this L, same base, you subtract the powers, therefore -1 minus -3 gives you +2. That is why you see a +2 there. Then this one is alone, so it remains as it is. Then from there, this power a half will simplify with this. 2 times negative times a half gives you 1, that's why there is power 1 there. Then -2 times a half gives you -1, that's why there is -1 there. After that, we shall conclude that since right hand side is equal to left hand side, it implies that the equation is dimensionally consistent. So that is how the marks will be awarded. So now we shall go to part C. Part C says, derive an expression for the energy stored in a stretched wire within elastic limit. So first we shall say that suppose a force capital F stretches a wire by an extension x within the elastic limit. What will happen is that work done is equal to average force. So here we use average force multiplied by extension. Average force is given by this because 0 plus F over 2. Why? Because when there is no extension at all, the force is 0, and when there is an extension x, the force is capital F. So average will be 0 plus F over 2, which will give multiplied by extension, which is x, and that will give you a half Fx. But we know that F is equal to Kx, where K is the force constant. Therefore, you come and substitute where there is F, we shall put there Kx to come up with a half Kx squared. So this is the expression they wanted, but you can also derive it using calculus. So in using calculus, we shall say, suppose extension small change in x is very small, so that the stretching force F is constant. What will happen? It implies that the small work done is equal to force times the small distance moved. Therefore, total work done will be given by the integral of F with the integrated with respect to x. So this small change in x becomes dx when you put an integral from 0 up to x, because it was stretched from 0 extension to an extension of x. Now when I integrate, I cannot integrate. I think we realize that this I have to integrate with respect to x, but this is f. So what do? I have to first express f with in terms of x. That is why I've come here and said that f is equal to kx. Therefore, I come and substitute for f, and in this case I can now integrate because the variable x is there. So when I integrate kx, I'll come up with a half kx squared, and that is what they wanted. So any of the two alternatives is okay. So now we shall go to part D. So part D says, a uniform wire of length 2.49 meters is attached to 2 points A and B, a horizontal distance 2 meters apart. When a 5 kg mass is attached to the midpoint C of the wire, the equilibrium position of C is 0.75 meters below the line AB. Neglecting the weight of the wire and taking Young's modulus for its material to be 2 exponent 11 newtons per meter squared, find Roman 1, the strain in the wire. So the first thing to do is to make a sketch of the given information. To help us is the calculation. So this is before they put a mass, and when they put a mass it has to be stretched further to this point here. So the weight is 5g newtons. Here there should be tension in the strings. The tension is the same because the natural length because natural length is the same. We have to first get some parameters. So AC prime. So AC prime, this distance is the same as this distance and can be got by Pythagoras theory, which gives you 1.25 meters. Therefore, the new length AC prime plus BC prime will be equal to this plus that, which gives you 2.5. So total length is from here up to here, and the original length is from here up to here. That means that you can easily get the total extension, which will be 2.5 minus the natural length, which was 2.49. So when I subtract the two, I'll come up with 0.01 meters as the total extension. Therefore, strain in the wire will be extension over original length, which will be extension is 0.01 and original length was 2.49, which gives you 4.0161 exponent negative 3. I think realize that there are no units on strain. So that was Roman 1. Now we shall go to Roman 2. Roman 2, they want the stress in the wire. So stress in the wire is given by Young's modulus multiplied by the strain. So I'll come and substitute Young's modulus and the strain. This is Young's modulus and this is the strain. Then you'll come up with 8.0322 exponent 8 pascals. So stress is the same as pressure. So that is how the marks will be awarded for this slide. So now we shall go to part D, Roman 3. So Roman 3 says they want you to calculate the energy stored in the wire. So first of all, you have to get the tan theta. Tan theta is OB over OC prime, which gives you the value of theta as 53.13 degrees. So when I resolve vertical, I'll come up with 2t cos theta is equal to 5g. Then substitute for theta and for g to remain with t as the only unknown. Therefore, t will be 40.8749 newtons. After getting T, I'll come and say that energy stored is a half TE, which is a half times T times the extension, which gives you 2.0375 exponent negative 1 joules. So that is how the marks would be awarded. So now we shall go to part E, Roman 1. So part E, Roman 1 says, sketch the stress strain curve for glass and explain its shape. So the first thing to do is to draw the axes, label them, then you draw the curve. It will be a straight line with a steep gradient, and that is what they wanted. But they also wanted you to explain this shape, so you have to say that glass obeys Hooke's law and breaks when stretched beyond the proportional limit. So that is why it stops here. It does not go ahead to do like that as for metal wire. So the reason is this because glass is full of cracks in its surface, and the high concentration of stress at the cracks makes it to break. So Roman 2, that was Roman 1. Now what about Roman 2? Roman 2 says, why does glass break easily? So this is somewhat like a repetition, but we shall still answer it. So it says, one of the reasons is glass is brittle and undergoes plastic deformation only. It does not undergo elastic deformation. The another reason is that the surface of glass has cracks in it. Therefore, a high concentration of stress on the crack makes it to break. So that is how the marks will be awarded for this slide. So that was question 2. Now we shall go to question 3. Question 3, A Roman 1 says, define centripetal acceleration. So here comes that centripetal acceleration is the rate of change in velocity for a body moving in a circular path. So that was Roman 1. What about Roman 2? Roman 2 says, show that the force capital F of a body of mass capital M moving in a circle of radius r with a constant velocity v is given by F equal to mv squared over r. So in this case, the good thing they have helped us to define the symbols or parameters. So if they had not, we would have written this as the introduction, that consider a body of mass m moving in a circular path of radius r and center O with a constant velocity v. Now in this case they gave us capital V, so we change that. Therefore the diagram will be as shown. So that is the velocity capital V from point A and it reaches point B. So suppose the particle travels from point A to an adjacent point B in time small change in t, and that the angle AOB is expressed in radians and is the small change in theta. So at point B, that will be the point with still the velocity the same because they said constant speed. It is only the direction which will change. Therefore, if I resolve that velocity horizontal and vertically, I'll come up with horizontal component as v cos the small change in theta and vertical component as v sine small change in theta. So that's how marks for this slide would be awarded. So next we have to say that centripetal acceleration is equal to change in velocity along AO from A to B over time taken to travel from A to B. So change in velocity, let's first go back to this diagram. Change in velocity along AO, because remember centripetal acceleration always acts towards the center. So along AO, at point A, this velocity is entirely horizontal, meaning that the vertical component is 0. But at this point, the vertical component is v sine small change in theta. Therefore, the change in velocity will be this minus 0, and the time taken will be this, which is small change in t. So you come here and substitute that acceleration will be equal to this change in velocity over time, where this is minus 0, so you come up with v sine small change in theta over small change in time. But we know that for small angles expressed in radians, sine that angle is equal approximates to that very angle. Therefore, acceleration will now become v small change in theta over small change in time. Then we also know that small change in theta over small change in time is equal to angular velocity, which is given by omega, and we also know that velocity or speed is equal to r omega. So we shall substitute both. Where there is this will be replaced by omega. Then after that we shall replace this omega with this, because we know that omega is equal to v over r, so to come up with v times v over r, which gives you v squared over r. Now if m is the mass of the body, centripetal force F will be given by F equal to ma, but A is already got as this, therefore F will be mv squared r, and basically that is what they wanted. So that is how marks would be awarded. So that was Roman 2. Now we shall go to part A, Roman 3. Roman 3 says, derive the condition for a car to move round a banked circular track without slipping. So slipping is the same as skidding. Now here they didn't define any parameter to be used, so we have to first define every parameter which we are going to use. So you have said that consider a car of mass m moving with a uniform speed v round a circular track of radius r banked at an angle theta as shown below. So you come and draw a sketch of the forces acting on the car. So we have the weight, which is mg, we have the normal reaction for this tire and also for this tire. Then by geometry, this angle is the same as this angle. Then centripetal force acceleration must act towards the center of the circular motion. So now that you have drawn the diagram, we shall come and say that the necessary centripetal force is provided by the horizontal components of the normal reactions. That means that when you resolve horizontally, this and this will give us the required centripetal force. So we shall come and say that r1 plus r2 in brackets sine theta is equal to mv squared over r. So that is equation 1. Then what about when we resolve vertically? So we shall say that since the car does not move off the road, it implies that when I resolve vertically, the vertical components of normal reaction will be equal to the weight of the car. So that's how the marks for this slide will be awarded. Now let's go to the next slide. So from equation 1 and equation 2, I'm going to divide the two equations to come up with that. Then from there, realize that this and this can cancel. Then this gives you tan theta. Then this m and this m can cancel, so you remain with tan theta equal to v squared over rg. Therefore, v is equal to square root of rg tan theta. So you shall come and conclude that for slipping not to occur, the velocity must be less than square root of rg tan theta. And that's how marks would be awarded. So now we shall go to part B. So part B says, describe how a helical spring may be used to determine the acceleration due to gravity. So the easiest thing is to first draw a sketch of the setup. So let's first draw that. So the meter rule is clamped and also the helical spring is clamped. And the helical spring is connected to a mass. So that's the diagram. Now we shall go and label the essential parts. So this will be the spring, helical spring. These are the masses. And this is the pointer. This is the retort stand. And this is the meter rule. So we shall start by saying that one end of a spring is clamped on a retort stand and a horizontal pin is fixed at the free end of the spring to act as a pointer, as you can see it here. After that, we shall say that the vertical meter rule is placed next to the pin and its initial position pin note noted. So this is the meter rule and the position is noted without the masses. So without this mass, we know the position, and that will be P naught. So after that, we shall suspend a known mass. So known mass M is suspended to the free end of the spring and the new position of the pointer P noted and recorded. So you suspend now a mass, then you record this new position P. After getting those two positions, you now get the extension from extension equal to magnitude of P minus P naught. So you put this magnitude to eliminate the negative in case it arises. After that, we have said that the mass is displaced through a small vertical displacement and the time for 20 oscillations T is noted. So before we go to the next slide, let's see marks for this slide, and that will be the marks. So now let's go and continue with the experiment. So the period T, capital T, is found and T squared calculated. After that, the procedure is repeated for several masses suspended in turns. A graph is therefore drawn of T squared against E and its slope calculated. Acceleration due to gravity G can then be got from this formula, which says that G is equal to 4 pi squared over S, where S is the slope. So that was part B. Now we shall go to part C. So part C says, a particle moving with simple harmonic motion has a speed of 8 meters per second and an acceleration of 12 meters per second squared when it is 3 meters from its equilibrium position. Find Roman 1 the amplitude of motion, then Roman 2 the maximum acceleration. So first of all, we know that acceleration is equal to negative omega squared x, but when you are substituting the calculation, you ignore the negative because the negative step is to help you know the direction. That acceleration and extension are in opposite directions. So acceleration is that, displacement is that, then we can now get the omega, which is the angular velocity. Therefore, angular velocity will be 2 rads per second. Then you also know that the v squared is equal to omega squared in brackets r squared minus x squared, where r is the amplitude, this is the angular velocity, and displacement from the equilibrium position. Therefore, you shall come and substitute. Velocity was that, angular velocity we have got it as that, displacement we don't know it, and x is 3. Therefore, I have only one unknown, which is r. Therefore, when I make it the subject, r will be 6.7082 meters, and that is the amplitude. So now shall go to Roman 2. For Roman 2, they wanted maximum acceleration. So acceleration is maximum when the displacement is maximum. Therefore, maximum acceleration will be equal when the displacement x is equal to the amplitude. So I'll come and substitute for omega, and for r, like I said, this negative is ignored in the calculations. So acceleration will now be 26.8328 meters per second squared. So that is how marks would be awarded. So that was question 3. Now shall go to question 4. Question 4 says, Part A, define the following: Roman 1, pressure, and Roman 2, relative density. So it comes that pressure is the force exerted normally per cross-section area of 1 meter squared. What about relative density? Relative density of a substance is the number of times a given substance is denser than water. Alternatively, you can say that relative density is the ratio of mass, or you can say ratio of weight of a given volume of a substance to the mass of an equal volume of water. So this word equal volume is needed. So that was part A. Now we shall go to part B, Roman 1. So B Roman 1 says, state Archimedes' principle. So Archimedes' principle states that when a body is fully or partially immersed in a fluid, it experiences an upthrust equal to the weight of the fluid displaced. So that is how marks will be awarded for this slide. So now shall go to part B, Roman 2. B Roman 2 says, describe an experiment to determine the relative density of a liquid. So you come and say that a sinker means an object which is denser than water. A sinker is weighed in air using a spring balance and its weight W0 noted. So you can illustrate it like that. So it's suspended in air on a spring balance and you measure its weight, and this weight will be W0. After that, we shall say that the sinker is fully immersed, note this word, fully immersed in water, and the new reading W1 of the spring balance is noted. So you can illustrate it like that. Now after measuring W1, the next thing is to get the upthrust of the sinker in water. So upthrust U1 of the sinker in water will be given by W0 minus W1. So you calculate it. Then the next is that the sinker is then fully immersed in a liquid whose relative density is required and the new reading W2 noted. After that, you also get the upthrust of the sinker in the liquid, and that will be U2, which will be W0 minus W2. So now the relative density of the liquid can be calculated from RD. So RD denotes relative density equal to out thrust in liquid over out thrust in water, which is W0 minus W2 over W0 minus W1. So that is how the 4 marks would be awarded. Now alternatively, we can also use the knowledge of moments. So in that we need a diagram. So this is also an alternative experiment for getting relative density of a liquid. So in this alternative, we shall say that a meter rule is balanced horizontally on a knife edge, and the balance point G, capital G, is noted. So this is the balance point. Other we shall say that a sinker A, which is this, is hung at a distance D from G. So without this liquid, you don't put this liquid there before, you just put a sinker A and you hang it at a distance D from G. Otherwise, that a standard mass B is hung from the opposite side and its position adjusted until the meter rule balances horizontally, while keeping G above the knife edge and D constant. So it balances, and let's see marks for this slide before I go to the next slide. So at that point you have to measure distance D0 of B from G. So this distance is measured from this distance between this from here up to here is measured when this one is alone and there is no liquid here. That is the first point. The next, the procedure is repeated with A in water and the distance D1 of B from G is noted. The procedure is also repeated for the liquid whose relative density is required, and the distance D2 of B from G is also noted. Then after getting those three distances, you'll come as the relative density of the liquid is obtained from RD equal to D0 minus D2 over D0 minus D1. So that is also an alternative experiment for getting relative density of a liquid. So now we shall go to part C, Roman 1. So Roman 1 says, derive the expression for Bernoulli's equation. So we need to define some of the symbols which will be used. So we shall come and say that consider an imaginary tube in a fluid between section X and Y, which are at heights h1 and h2 from the reference line as shown below. So let's first illustrate that information. So that is the reference line, then that is the tube. Then we have point X and also point Y. So point X is at a height h1. What about point Y? Will be at a height h2. So we have to define all the symbols. So we shall say that let P1 and P2 be the pressure, and V1 and V2 be the velocities, and A1 and A2 be the cross-section areas at points X and Y respectively. So P1 is for point X, P2 is for point Y, A1 is for point X, and A2 is for point Y. So at point X we have area A1 and velocity v1 and also pressure p1. What about point y? Point y, you have area a2, velocity v2 and pressure p2. So have a mark for defining the symbols to be used. So now let's go to the derivation part. So work done per second is equal to, first of all, we need to know that work done per second is force times velocity, which will be force is AP, area times pressure, and velocity is V. Now once we know that, we shall come and state the conservation of energy, that change in work done per second per unit volume is equal to gain in kinetic energy per second per unit volume plus gain in potential energy per second per unit volume. Therefore, come and substitute. Work done is force times work done per second is this as APV. So change in work done will be work done at point X minus work done at point Y over volume. Then gain in kinetic energy will be kinetic energy at point Y minus kinetic energy at point X. Gain in potential energy will be potential energy at point Y minus potential energy at point X. So the good thing, we know that mass per second is density times area times volume. Therefore, rho is the density, A is the area, and V is the volume. So what does that mean? We are going to substitute this with this expression, and we shall come up with that. So the volume must cancel this because it is constant throughout. So where there is M2, we shall put there this. I think we see that now it is tubed because in this one there is rho AV and there is also V squared here. That is why it is now tubed here and tubed there. So we should begin with that. So this M2 will be that, and this M1 will be that, because density is the same. So that you shall remember that AV is constant. So area times velocity is equal to, at point X is equal to area times velocity at point Y. I think you remember that. So before we go to the next slide, let's see mass for this slide, and then we can go to the next slide. So this one means that AV can cancel throughout. So when I cancel AV throughout, I'll come up with that. Then when I rearrange, I'll come up with that. Rearrange parameters of X alone and parameters of Y alone. So what does that mean? It means that P plus a half rho V squared plus H rho G is constant, and that is Bernoulli's equation. So now we shall go to part C, Roman 2. Roman 2 says, explain why a person standing by the roadside may be pulled towards the road when a very fast moving bus passes by. So yes, that as the bus passes, it makes the air between the man and the bus to move with a high velocity. The air between the man and the bus is at a high velocity. What about the air behind the man? It is at a low velocity. So what does that mean? It means that by Bernoulli's principle, there is a low pressure between the man and the bus and a high pressure behind the man. So what does that mean? It means that pressure difference causes a net force that pushes the man towards the bus. So that is how marks will be awarded for that slide. So now we shall go to part D. So part D says, a watertight drum tied to a cable anchored on the seabed floats 500 meters beneath the sea surface as shown in figure 1. If the weight of the drum is 500 newtons and its volume is 25 meters cubed, calculate Roman 1 the pressure on the drum due to the sea water. So we're going to first redraw the given diagram, then we show the forces acting on the drum. So now we can show the forces. The first force will be the weight, which is 500 newtons. Then next will be the pressure acting downwards, then also the upthrust acting upwards, and the tension in the string. Okay, so now we can go to Roman 1. So pressure is equal to pressure P1 or P, this can be just P, is equal to H rho G, where H is 500 meters, then rho is constant, density of water, and G is 9.81. So when I simplify this, I'll come up with 4.905 exponent 6 pascals. So that was Roman 1. Now we shall go to Roman 2. Roman 2, the one tension in the cable, assuming it is vertical. So volume of water displaced is equal to volume of the drum from Archimedes' principle, so it will be 25 meters cubed. Then upthrust in water will be equal to volume displaced multiplied by the density of water multiplied by acceleration due to gravity. And that will be volume is 25. I've already seen that. This is a constant and this is also a constant. So it will be 2.4525 exponent 5 newtons. So that is the upthrust to U. So for this slide, that's how marks would be awarded. So when the cable is vertical, it implies that upward forces are equal to downward forces. Therefore, upthrust is equal to weight plus tension. So you are going to substitute upthrust here, weight here, and tension here. So when I make T the subject, T will be 2.4475 exponent 5 newtons. So that was question 4. Now we shall go to question 5. Part A says define the following: Roman 1, triple point of water, and Roman 2, absolute zero temperature. So you come as that triple point of water is the unique temperature at which pure water, pure melting ice, and pure saturated vapor coexist in equilibrium. What about absolute zero? So you come and say that absolute zero is the temperature attained when molecules slow down and acquire the least possible energy. So that was part A. Now we shall go to part B. Part B says explain why triple point of water is taken as a standard in modern thermometry instead of ice and steam points. So you come and say that triple point of water is a single temperature and a single pressure. What does that imply? It implies that for ice point and steam point, these are 2 points and they vary with pressure and level of impurities. And that explains why triple point is used more instead of ice and steam point, because these ones vary with pressure and level of impurities, while triple point is just a single temperature. So that's how marks would be awarded. So now we shall go to part C, Roman 1. So Roman 1 says, what is a thermometric property? So you can answer that a thermometric property is a physical property of a substance whose value varies linearly and continuously with temperature. So now we shall go to Roman 2. Roman 2 says, state three qualities of a good thermometric property. So the first one is that it should vary over a wide temperature range. The next, it should vary linearly and continuously with temperature. Next is that it should be sensitive to temperature changes. Next is that it should give a single value for a single temperature. Next is that it should accurately be measurable over a wide range of temperature for a single apparatus. So that is how marks would be awarded. So now we shall go to part D, Roman 1. So part D, Roman 1 says, a constant volume thermometer was used to measure temperature when the atmospheric pressure was 760 millimeters of mercury. The following values were obtained. So this is the length of the mercury in closed limb, and this is the length of the mercury in open limb. So bulb in ice is that in closed and this in open. So these are the values for steam and also for room temperature. Then they said calculate the room temperature. So pressure at ice point is that capital H, which is atmospheric pressure, minus the difference in mercury levels in both limbs, which is this. So we'll come up with 750 millimeters of mercury. What about at steam? So it will be that this plus this to give you this plus the difference in mercury limbs, which is that. Then at an unknown temperature, it is this, which gives you that. So after calculating that, you'll come and say that the temperature will be equal to P theta minus P naught over P 100 minus P naught, everything multiplied by 100. So I'll come and substitute for P theta, P naught here and here, then P 100 here. And in the end, I'll come up with 20 degrees Celsius. So that was Roman 1. Now we shall go to Roman 2. So Roman 2 says, list two advantages of the constant volume gas thermometer over mercury glass thermometer. One is that it can be used over a wide range of temperature. Then two is that it is very accurate and therefore can be used as a standard to calibrate other thermometers. Then three is that it is very sensitive and therefore it can be used to measure very low temperatures. So that is how marks would be awarded. So now we shall go to part E. Part E says, explain what happens when the temperature of a fixed mass of ice is raised from 0 degrees Celsius to 10 degrees Celsius. So here we have to remember the anomalous expansion of water. Therefore, just that at 0 degrees Celsius, the bonds between the ice molecules are weakened and ice melts. Between 0 and 4 degrees Celsius, water contracts. Then beyond this temperature, water expands. So that is the anomalous expansion of water. It first contracts, then expands. So that is how the marks would be awarded. So now we shall go to question 6. Part A says define specific heat capacity. So specific heat capacity is the quantity of heat required to raise the temperature of a 1 kilogram mass of a substance by 1 Kelvin. So that was part A. Now we shall go to part B. Part B says describe, stating the assumptions made, an electrical method for the determination of the specific heat capacity of a metal. So the first thing to do is to draw a diagram to help us is the theory part. So you are complete step by step. So this is a solid metal and with an insulation around it. So you start by saying that 2 holes are drilled in a metal block and its mass M measured and recorded. So we shall drill 2 holes in a metal block, and this is 1 hole and this is another hole. Then after that we shall say that a thermometer is inserted in one of the holes and an electric heater in the other. So you shall first insert the thermometer in one of the holes. So that's the thermometer. Then the other hole will have a heater. So a heater needs to have a power source. So let's first draw a circuit for the power supply. After which you shall now draw the heater in the hole. Then after that we shall say that holes are then filled with a conducting fluid and the apparatus is insulated. So this is the insulation. So for this slide, these are the marks. Now we shall go to the next slide and continue with the experiment. So we have said that the initial temperature θ1 is recorded. Then after that we shall say that the heater is switched on and the stop clock started simultaneously. So they are started at the same time. The voltmeter and ammeter readings V and I respectively are noted. After a considerable temperature rise, the heater is switched off and the stop clock stopped simultaneously. The highest observed temperature θ2 of the block is read and recorded, and the time t for which the heater was on is noted. The specific heat capacity of the metal block is now calculated from the formula that C is equal to IVT over M in brackets θ2 minus θ1. So that's how the marks will be awarded for this slide. But remember, they also talked about the assumptions made. So the assumption you have said that it's assumed that 1. Heat lost to the surrounding is negligible. 2. The quantity of heat gained by the thermometer and the heater is negligible. 3. The volume of the solid block is constant, hence there is no work done against atmospheric pressure. In other words, it doesn't expand. So that was part B. Now we shall go to part C. Part C says, in an experiment to determine specific heat capacity of a liquid using the continuous flow calorimeter, Roman 1, the readings are taken when the apparatus has attained a steady state. Explain the meaning of a steady state. So here come and say that steady state is the condition when the inflow and outflow temperatures are constant and the heat loss to the surrounding heat is lost to the surrounding at a constant rate. So that was C Roman 1. What about Roman 2? Roman 2 says explain why two sets of readings are taken. So you come and say that the two sets of readings are taken to account for the heat losses to the surrounding during steady state. So that is how marks would be awarded. So now we shall go to part D. Part D says when water is passed through a continuous flow calorimeter at a rate of 100 grams per minute, notice what it is per minute, the temperature rises from 16 to 20 degrees Celsius when the PD across the heater is 20 volts and the current is 1.5 amperes. When another liquid at 16 degrees Celsius is passed through the calorimeter at the rate of 120 grams per minute, the same temperature change is obtained at a PD of 13 volts and current of 1.2 amperes. Calculate the specific heat capacity of the liquid. So let's see to be the specific capacity of the liquid which is required, and H be the rate of heat loss to the surrounding. Remember the mass was given per minute, but we want it in terms of per second. So you come and say mass per second of water flowing will be 1/600, that is kilograms per second. And what about the mass of the liquid flowing per second will be that 2 exponent -3 kilograms per second. It was grams per minute, so we have converted from grams per minute to kilograms per second. After that, we have come and said by conservation of energy, I1 V1 is equal to M1 C1 change in temperature plus H. So this is for the first set for water. What about for the liquid? So for the liquid it is I2 V2 equal to M2 C2 change in temperature plus H. So that's how mass will be awarded for this slide. Now we have to use these two equations to come up with the value of C2. So when I subtract the two equations, I'll come up with that. And when I substitute for each parameter, I'll come up with I1 is that, V1 is that, I2 is that, V2 is that, M1 is that, C1 is that, change in temperature is that. Then M2 is that, C2 is not known, change in temperature is that, because it was from 16 to 20. So I have only one unknown, therefore when I simplify and make it the subject, C2 will be equal to 1700 joules per kilogram per Kelvin. So that's how the marks will be awarded. And now shall go to part E Roman 1. So E Roman 1 says define latent heat. So latent heat is the quantity of heat required to change state of a substance to another state at the same temperature. So here it is not it should not be 1 kilogram, but if there is the word specific latent heat, the mass should be 1 kilogram. So that was Roman 1. What about Roman 2? So Roman 2 says, explain why latent heat of vaporization is always greater than that of fusion. So I comments that in vaporization, heat is required to break intermolecular attractions between the molecules of the liquid in the surface and the bulk of the liquid, and also for vapor to expand and do work against atmospheric pressure. But for fusion, energy is only needed to weaken the intermolecular attraction. So that explains why they cannot be of the same value. So that was question 6. Now we shall go to question 7. So part A, Roman 1 says, explain how a thermocouple is used to measure temperature on a Celsius scale. So the thermometric property is EMF over thermocouple. Then we shall come aside that the cold junction of the thermocouple is maintained at ice point. What about the hot junction? So it's the hot junction which is moved from place to place. Therefore, the values of EMF of the thermocouple E100 and E0 at steam and ice points respectively when its hot junction is placed in steam and ice respectively are noted. So this one is when the hot junction is placed in steam, and this is when the hot junction is placed in ice. The hot junction is then brought into contact with an unknown temperature theta, and the corresponding EMF E theta is noted. The unknown temperature theta is then obtained from theta equal to E theta minus E0 over E100 minus E theta, everything multiplied by 100. So that is how marks would be awarded. So now shall go to Roman 2. Roman 2 says, state 2 advantages of a thermocouple. So one is that it can measure temperature at a point. Then 2 is that it is very sensitive to temperature changes. Then 3, it is portable. And 4, it has a wide range of temperatures. So that was part A, Roman 2. Now we shall go to part B, Roman 1. So B, Roman 1 says, two cylindrical bodies A and B are made of the same material, but the length of A is twice that of B, and the cross-section area of B is a third that of A. If the ends of A and B are subjected to the same temperature difference, find the ratio of the rate of heat flow through A to the rate of heat flow through B. So for the same material, it implies that coefficient of thermoconductivity is the same. They also gave us the length. This length of A is twice that of B, so this will be 2L and this will be L to give you 2. What about the area? Area of A was that, and area of B was the third that of A, so we'll come up with 3. So that's the marks for this slide. Now let's go to the next slide. So the rate of heat flow through A is dQ1 dt, which is given by that formula. Then the rate of heat flow through B is given by that formula. So when I divide the two, because I wanted the ratio, I'll come up with that. Then when I simplify, I'll come up with this, because this cancels, so this divided by this is this, and this divided by this is that. So in the previous slide we saw that this is 3 and this is a half, so we'll come up with 3 over 2. Therefore we'll conclude that the required ratio is 3 to 2. So now we shall go to part B, Roman 2. Roman 2 says, in the determination of thermoconductivity of copper, when water flows round the cool end of a copper rod at a rate of 600 centimeters cubed per minute, its temperature increases by 3.3 degrees Celsius. The temperature at 2 points, a distance of 5.2 centimeters apart, along the copper rod are 70 degrees Celsius and 30 degrees Celsius respectively. Find the thermoconductivity of copper if the radius of the rod is 1.2 centimeters. So you come and say that the mass of water flowing per second is volume per second multiplied by density. So that gives you 0.01 kilograms per second. So that's how marks will be awarded for this slide. Now let's go to the next slide. So rate of heat gained by water is equal to rate of heat flow through copper. Therefore rate of heat gained by water is mc change in temperature, and rate of heat flow through copper is Ka. So A is pi r squared is area, change in temperature over L, which is the thickness. So I'll come and substitute for M. I've already got it as this. C is that constant, this is that regular in the question. This K is not known, pi is there, R is there, T squared, change in temperature is that, and thickness is that. So in this case we realize that K is the only unknown, therefore when I simplify I'll be able to get K as 3.9829 exponent 2 watts per meter per Kelvin. So that's how marks would be awarded. So now we shall go to part C. Part C says describe an experiment to measure thermoconductivity of copper. So it is easily done when we draw a diagram. So let's first draw a diagram to ease the description. So next is to label some of the parts. So this is the steam chest, and that is steam in, and this is steam out. This is brass slab X, that is the coke, and this is the brass slab Y. So now that is the diagram. Now we can start our description. So you have said that coke is made into a thin wide disc, and its diameter D and thickness L are measured and recorded. The disc is then put between two brass slabs X and Y, each carrying a thermometer, as you can see them here. The disc and brush surfaces are smeared with a thin layer of grease for better thermal contact. Steam is then passed through the steam chest until the thermometers T1 and T2 show steady values. So these thermometers, the readings will keep on increasing until they give a constant reading. So at that point, the steady temperatures theta1 and theta2 respectively are recorded. After recording, the disk is removed and slab Y is heated directly when in contact with slab X until its temperature is higher than theta1 by say 10 degrees Celsius. So we are going to remove this coke so that there is contact between this and this, and it will be heated until the temperature is higher than that of theta1. So for this slide, that's how marks will be awarded. So let's go and continue with the experiment. So the steam chest is then removed and the disk is placed on top of slab Y. The temperature of slab Y is recorded at suitable regular time intervals. A cooling curve is then plotted, and the slope S of the graph at theta1 is obtained. The mass M of slab Y and specific capacity C is determined, and after that we can now calculate the thermal conductivity of coke using this formula. But remember, they want K, so what I'm going to do, I'm going to make K the subject, which will give me K is equal to 4 mc/SL over pi d squared change in temperature. So that's how marks would be awarded. So that was question 7. Now we shall go to question 8. So question 8 part A says, what is meant by the following as applied to radioactivity? Roman 1 activity and Roman 2 decay constant. So activity is the number of disintegrations per second of a radioactive sample. What about decay constant? So decay constant is the fractional number of disintegrations per second of a radioactive sample. So now shall I go to part B. B Roman says, explain briefly why radioactivity is referred to as random and spontaneous. So it is random because one cannot tell which nucleus is going to disintegrate next, and it is spontaneous because the rate of decay cannot be controlled by physical or chemical change. So that's how marks would be awarded for this slide. So now shall go to part B Roman 2. Part B Roman 2 says the half-life of thorium 230 is 2.4 exponent 11 seconds. Find the number of disintegrations per second that occur in 1 gram of thorium 230. So first of all, the decay constant is given by that formula, ln 2 over half-life. So kama substitute ln 2 is there, half-life is there, to come up with that as the decay constant. The number of atoms will be mass over molecular mass multiplied by Avogadro's number. So for thorium it was thorium 230, so molecular mass will be 230, and mass was given as 1 gram. So Avogadro's number is a constant as given in the table of constants. So we'll come up with this as the number of atoms. Therefore, the activity will be equal to decay constant times the number of atoms to give you substitute for decay constant and number of atoms to come up with this as your activity. So now we shall go to part C, Roman 1. So C Roman 1 says, describe with the aid of a diagram how a Wilson cloud chamber can be used to detect ionizing radiation. So we have to first draw a diagram. So we need to label some of the parts. One will be this as illumination, then this is the camera, this is the saturated vapor, then this is the glass plate, this is the radioactive source, dark pad soaked in alcohol, and this is the piston. So that's how marks will be awarded for this slide. So the setup is as shown above. With alcohol on the dark pad, the piston is moved down quickly so that the air in the chamber undergoes an adiabatic expansion and cools. After a few expansions, the dust particles are all carried away by the drops forming on them. The dust-free air is then subjected to controlled adiabatic expansion. The air becomes supersaturated, and simultaneously the air is exposed to radiations from a radioactive source which ionizes it. Water droplets immediately collect around the ions, producing tracks which are viewed through the glass plate. The tracks produced are then illuminated and photographed by the camera. So that is how marks would be awarded. So now we shall go to part C, Roman 2. Explain the difference in the patterns of the tracks seen in the chamber when alpha and beta particles are present in the chamber. So here comes that alpha particles produced thick, short and straight tracks compared to thin, long and tortuous tracks produced by beta particles. So the reason is that alpha particles are more massive and slower compared to beta particles, which are less massive and therefore easily deflected after collision with gas molecules. So that was part C. Now we shall go to part D. So part D, Roman 1 says, what is meant by mass defect? So mass defect is the change in mass when the nucleus of an atom splits into its constituent particles. Alternatively, you can say that this is the difference between the mass of nucleons and mass of nucleus of an atom. So that is how mass would be awarded. Now we shall go to part D, Roman 2. D Roman 2 says, calculate in mega electron volt the energy released when helium nucleons are produced by fusing 2 neutrons and 2 protons. So these are the masses. So you have to first balance the equation. So this is the equation which has been given. Therefore, you come and substitute. The mass unit for neutron was given as that. For this one it was that, and for this one it was that. And this one to just is not known, so it will be given by changing m. Therefore, making this the subject, it will be equal to 0.03037 U. But we know that 1 U is equal to 931 mega electron volt. Therefore, energy released will be equal to this times this, which gives you 28.27447 mega electron volt. So that is how mass would be awarded. So that was question 8. Now we shall go to question 9. Question 9a, Roman 1 says, what is meant by p-n junction as applied to semiconductors? So a p-n junction is one formed by melting the boundaries of a p and n-type semiconductor and joining them. So that was Roman 1. Now we shall go to Roman 2. Roman 2 says, explain the term doping as applied to p-n junction diode. So doping is the introduction of controlled amounts of group 5 impurities into 1/2 of group 4 semiconductors and group 3 impurities in the other half of group 4 semiconductors. The first half has electrons as majority charge carriers and therefore is called n-type, while the second half has holes as majority charge carriers and therefore is called the p-type. So that is how marks would be awarded. So now we shall go to part B. So part B, Roman 1 says, explain with the aid of a diagram the IV characteristic of an overjunction diode. So we shall draw the axis, then Remember, you have a part which is forward biased and a part which is reverse biased. For the forward biased, it will be of that shape, and reverse biased, it will be of that shape. So they told us to explain such as that when the PN junction diode is connected to a forward bias, there is a large flow of electrons and hence high current. That's why you see this is high, steep. However, in reverse bias, there is a small current due to minority charge flow. That is why the current flowing is very small. So that is how marks would be awarded. So now we shall go to part B, Roman 2. Roman 2 says, describe how full wave rectification can be achieved using a bridge rectifier. So we shall need to first draw a circuit diagram of a bridge rectifier. So that is the circuit diagram. Now we can easily explain. So we shall come and say that during the positive half cycle of the AC input waveform, point A is made positive with respect to point B. So this is positive with respect to B. What does that mean? It means that diodes D2 and D4 conduct, and current from the source follows the path A, X, Y, B, and then back to the source. So how do you know where the path taken? So in a layman's language, you shall say that you follow the arrow. So the arrow goes in this direction. But this arrow goes in this direction. Therefore, if current comes from here and reaches here, it can't go in this direction because of this arrow. That is in the layman's explanation. So it will follow this arrow, therefore it will go in this direction up to here. Then when it reaches here, you realize that this arrow goes in this direction, so it can't take that path. Therefore it will take this path up this point, and from this point it has to go this side. So one would ask, why doesn't it go this direction? It can't go because this is where it comes from, and to complete the circuit it has to end here. Therefore it has to go, the only option is to go this side and then go this side and then back to the source. So the current takes on the direction of this. From here it comes here, it goes here, then here, then here, and back to the source. So it takes the direction A, X, Y, B, and back to the source. Therefore through the load it will be in that direction. That is for the positive half cycle. What about for the negative half cycle? For the negative half cycle, B is made positive with respect to A. What does that mean? It means that current will come in this direction. When it reaches here, it can't go to D4, so it will have to go to D3, then go to this, go to this, go to this, and back to the source. So you come and say that diodes D1 and D3 conduct, and current from the source follows the path B, X, Y, A, and then back to the source. So that means that it takes this direction. Remember also previously the direction was XY. Therefore we shall come and say that in both cycles, current flow through the load is in the same direction, and hence AC is fully rectified. So that is how marks will be awarded. So now shall go to part C. Part C says the input resistance of a certain NPN transistor in the common emitter connection is 3 kilo ohms. The small current amplification transfer ratio is 100. The internal resistance of the emitter base junction is negligible, and the load resistor is 6 kilo ohms. Find the voltage gain. So voltage gain mu is given by beta in brackets RL over RI plus RS. So this is that 100, and this was given as 6 kilo ohms, so to change to multiply by 1000 to get ohms. This one also 3 kilo ohms. This one was negligible, so it is 0, so in the end we'll come up with 100. So it has no units because it's a ratio of resistance. So now shall go to part D, Roman 1. So D Roman 1 says, explain the mechanism of thermionic emission. So metals contain free electrons in the lattice. When the metal is heated to a high temperature, electrons gain kinetic energy. Those electrons whose energy is sufficient to overcome the attractive forces of the positive nuclei leave the surface and the metal, implying thermionic emission. So that is how marks would be awarded. So now shall go to part D, Roman 2. Roman 2 says, the gain control of a cathode ray oscilloscope is set to 0.5 volts per centimeter, and an alternating voltage produces a vertical line of length 2 centimeters with the time base off. Find the root mean square value of the potential difference. So they want VRMS. So first of all, peak to peak will be given by this, the PD per centimeter multiplied by the length, which gives you 1 volt. Therefore, peak AC voltage will be half of the peak to peak, which will be 0.5 volts. And root mean square was given by peak voltage over root 2 to come up with, so peak voltage is 0.5 divided by root 2, you'll come up with 0.3536 volts. So that is how marks would be awarded. So that was question 9. Now shall go to question 10. Question 10, part A says, define specific charge of a positive ion and state its unit. So specific charge of a positive ion is the ratio of charge on an ion to the mass of the ion. So charge to mass ratio is specific charge, and the unit is coulomb per kilogram. So any of these two is okay. So that was part A. Now shall go to part B. Part B says, with the aid of a labeled diagram, describe how Bain bridge spectrometer can be used to determine the specific charge of positive ions. So this can be easily answered with the aid of a diagram. So let's first draw the diagram. So this diagram is not complete, but we are complete step by step as we go through this theory part. So let's first see line 1. So line 1 says, positive ions are produced in the discharge tube and get accelerated to pass through slits S1 and S2. So let's first show now the discharge tube. So that section is what we call the discharge tube. It will have gas here and also electron beam here and a positive plate here and a negative plate there. Then we shall say that these positive ions enter the velocity selector chamber where they are acted upon by crossed magnetic and electric fields of flux density B1 and intensity E. So we have to show the slits S1 and S2 and also the velocity selector. So that is the ion accelerator. It accelerates the positive ions which are formed in this discharge tube to pass through this. So the velocity selector is this part. This chamber is what we call the velocity selector, and like they said, it contains crossed magnetic field of flux density B1 and also electric field. So we shall show the electric field by those two plates, positive and negative, and also magnetic field B1. So that is the velocity selector, and these are the positive ions through slits S1, S2 and to the velocity selector. So at this point, what happens next? Let's see line 3. So line 3 says, only ions with velocity v such that B1 chu v is equal to E chu pass through the velocity selector and deflected, and enter the momentum selector where a magnetic field of flux density B2 is applied. So that means that these ions which are undeflected have the required velocity, and the ones which don't have the required velocity will be deflected away will be deflected. So the momentum selector is the whole of this, is this chamber here, and it has a magnetic field of flux density B2. So we shall come and show that B2. So that is line 3. What about line 4? Line 4 says, the ions describe a circular path in the momentum selector and strike the photographic plate with a velocity v. So let's first show that. So these ions will follow a circular path and strike the photographic plate at different points because they have different masses. So that was line 4. What about line 5? So line 5 says the radius r of a particular selected ion of mass m is measured on the photographic plate and recorded. So let's show that. So of these three, you choose one and measure the radius of the circular path, so that it will be r, which is this. So that is the marks for this slide, but the experiment is not yet complete. So let's also see marks for this diagram before we complete the experiment. Okay, so now we can go and complete our experiment. So we shall come and say that here we need some calculations. So magnetic force provides the necessary centripetal force for circular motion to occur. So when I make Q over m the subject, remember they want charge to mass ratio. So bring this m this side and these others go this side to come up with Q over m equal to V over B2R. But also previously we saw that B1 Q V is equal to EQ. Therefore when I make V the subject, I'll come up with, you realize that Q cancels, so remain with V equal to E over B1. So when I substitute this V here, I'll come up with that as the charge to mass ratio, or the specific charge of the positive ion. And basically that is what they wanted. So now we shall go to part C. Part C says, a beam of positive ions accelerated through a potential difference of 2000 volts enters a region of uniform magnetic flux density B. The ions describe a circular path of radius 3.2 centimeters while in the field. If the specific charge of the ions is 8.5 exponent 7 coulomb per kilogram, derive an expression for the charge to mass ratio of the ions and use it to calculate the value of B. So first we know that electric work done is equal to kinetic energy gained by the ions. Therefore electric work done is charge multiplied by accelerating voltage, and kinetic energy is a half mv squared. Therefore make V the subject, I'll come up with that expression. Then also I know that magnetic force is equal to, provides the necessary centripetal force, so B2V is equal to mv squared over r. Simplify V, you remain with one V here. Then take this R this side to come with B2R equal to mv. When I substitute for V, remember V is that, so put it here to come up with that. So to remove the square root, I have to square both sides. I'll come up with that. Then rearrange, because this one and this one cancels, remain with 1 Q over m, which is that. Then this one goes this side to come up with B squared over R squared here, and this one remains as that, the numerator. Therefore charge to mass ratio is that. So that is how marks will be awarded for this slide, but remember they told us to use the given derivation to get the value of B. So we shall go here and say that for the hence part we shall come and substitute this, that, and that. So we remain with only B as the only unknown. Therefore I'll make B the subject, and B will be equal to 0.2144 Tesla. So that now we shall go to part D. So part D says, state the use of each of the following features of cathode ray oscilloscope. Roman 1 anode system, Roman 2 Y plates, Roman 3 grid. So the anode system accelerates and focuses electrons. What about the Y plates? So the Y plates deflect electrons vertically. And lastly the grid. So the grid controls the number of electrons striking the screen per second and hence controls the brightness of the image on the screen. So that is how marks would be awarded. So now shall go to part E. Part E says an electron with energy 5 kilovolts moves in the direction of an electric field intensity of 1.6 exponent 4 volts per meter. What distance will the electron move before coming to rest? So now that electrical work done is equal to kinetic energy gained by the electron. Therefore, charge of an electron multiplied by voltage is equal to a half mv squared. So this v is velocity, this is voltage. So I come and substitute. This E is a constant, and this one was given as 5 kilovolts. So you change it to volts to become 5 exponent 3. Then mass is also a constant, mass of an electron, and this is unknown. So I think we realize that V is the only unknown, so I can make it the subject. Therefore, V will be equal to 4.1908 exponent 7 meters per second. So also we know that F is equal to MA, so when I substitute F will be equal to negative E, electric field multiplied by the charge, electronic charge, and MA equal to MA. So know that there is a negative here, because it is coming to rest, meaning it is under deceleration. So that's how marks will be awarded for this slide. So let's go and continue with the calculation. So substitute for electric field intensity and the electronic charge, mass, and acceleration is the only unknown, so I can easily get the value of A. The value of A, which is the acceleration. I think you realize that this has a negative because it is retarding. Now using the equation of motion, I can come and substitute final velocity is 0. Initial we got it as this. Acceleration we have got it as that. S is what we want. So when I make S the subject, S will be equal to 3.1215 exponent negative 1 meter. So that is how marks would be awarded. So that brings us the end of this video. Thanks for watching, and be reminded the next video will be on marking guide for physics paper 2 of UNEB 2020. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on the solutions for physics paper 2 has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.